guest speaker is an old friend of mine. We work together with John Deere. Mike Langner is a metallurgist, and we relied on him for years to keep the gears right and the cast iron correct and the crankshafts holding together. And he looked after all that. He's probably cut out many, many millions of silver blocks and crankshafts. Anyway, if you have any questions on all the way from the old steel all the way up to the new powder metal stuff, Mike has the answers. But feel free to ask questions.
Put that there. Yeah. Closer the better.
Closer the better. Okay. Can you hear me?
One more light.
Is that okay? Am I blocking anybody?
So if you turn all these off, just leave that alone over there. One more time. And off it. They don't. It's pulling the light over.
Okay. Like I said, anytime during this talk, stop me. If you want any details, I can go into any details you want. I'm trying to do somewhat of an overview of steels, and if you go through history, your basic steels were 100 years ago, were plain carbon. And that's what most of your tools were made out of. Now they tended to be higher carbon. They were like a 0.6 to a 0.9 carbon. They had very little alloy in them. They were easy to heat treat, easy to sharpen. The problem is they tended to get dull very soon and required a lot of sharpening. The microstructure, it transforms. It is pretty much homogeneous. It is the same hardness all the way through. And it doesn't have a lot of alloy in it to give it enhanced properties like toughness, wear resistance, etc. So the next development they came into were your high-speed steels. There again, here are some of the basic characteristics. High attainable hardness, very hard, Rockwell C. Rockwell C, a very hard knife is in your Rockwell C 61, 62, 63 type for a reference. If you have like a scraper, something like that that's flexible, those are Rockwell C 52, 53. Relative comparison. Yes?
How do they test for hardness?
Hardness, what they do is they have a diamond pyramid tester. You apply a given load, it impacts, comes into the surface. When you back it off, you measure the amount of the depth of the indentation, and that's what the hardness of the material is. So Rockwell C60, that's a very good gear like you'd find in a car or a tractor. A very good sharp knife, hard knife. They don't sharpen overly well, but it's very nice for hardness. It's very wear resistant, your high-speed steels. And depending on which one, they have impact toughness. And I'll go into some of the differences there. And it also resists tempering. At high temperatures, if you take a carbon steel, let's say like a 0.8 carbon steel, harden it to Rockwell C60, if you heat it up when you're sharpening it to a blue color, it's about a Rockwell, or that's a 550, 600F, you'll lose, it'll go from like Rockwell C60 down to 55. It doesn't resist the temperatures. Your tool steels are made to resist the temperatures. like these are high-speed steel. So that's one of the reasons they've gone to your tool steels. Here are some of the properties of tool steels. You can see the one on the far left is like an S7. It's a shock resisting. You made chisels, etc. out of it. You can see it has very good toughness, hardness 58, which is quite good. And the wear resistance, pretty low. As you go across your old ones, those are very similar to your plain carbon steels, the older, high carbon steels. You go across, you have an air hardening steel, a D2, I can't remember exactly what that one. Your M2s and M4s are used a lot in woodworking tools, as well as your 10V and at 2 different hardnesses. Now those are, last two they're a powdered metal. They take atomized powder, compress it, center it, and make a tool out of it. A lot of your M4s, rather than going with the wrought product, they make them out of powdered metal, and I'll explain that in a minute. Here are the typical chemistries. You can see the A1, it has a good shot of chrome and some moly, or the A2. Your M2, M4s, your major ones are chrome. In fact, all of these have high chromes. Chromes are nice because they form carbides. You have chrome carbides, another carbide former is your vanadium on the right. Tungsten, it also forms carbides. Moly is more of a strengthener, and it adds some toughness to the matrix. It generally doesn't form carbides. And all of those, when you make your steel, add certain properties to it. Okay, let's see what the next one. Here's some surface treatments you can put on. A lot of your tools have various surface treatments, some enhancements. Some of your basic, a nitride. That's a gaseous treatment. Heat them up to about 900 F. You diffuse it into the surface. It's a hard, wear-resistant, anti-galling. Tends to be low cost. Your next one, TIN, titanium nitride. The gold-colored stuff. Put it in the furnace. It is actually a physical vapor deposition. It's a very thin layer, anti-galling, abrasion resistance. It'll hang around for a while. Then same material, just different process. And then you go the TICN, that's a complex. It's a titanium carbonitride surface. A little harder, a little more exotic. It provides a lot of abrasion resistance and anti-galling. Yes?
When you talk about surface treatment, how much of a layer are you putting on?
We're thinking very, very thin, a few microns.
Microns?
Yeah, very, very thin. They tend to be very brittle, and if you build up too big of a layer, they'll spall off and crack if you impact them. Yeah.
One of my Chinese titanium drills, do I get something this good compared to those, or is it worse?
I've looked at some, and they're gold in color. There isn't very much on there. Yeah. You can put, they got most of it covered. Yeah. But typically they don't put it on, generally when you're cheap drill bits, they tend to be high carbon steel. They put the titanium on them to look nice, and they're good for a few holes.
If I have a titanium, a real good drill, and I sharpen it in a drill doctor, it takes the titanium off the tip.
It'll take it off the flutes and stuff, yes.
Does it work?
You still have it on the sides for galling, etc. So you lost part of it. If you were an industrial, some places it's important on the cutting edges, so they'll actually take them back and re-nitrate them. Go put another coat on them, grind them, take a whole batch, and titanium nitrate them. Yes?
Would that type of coating be beneficial on like even carbide?
They do put it on some carbides. They coat them. It's just a slight enhancement. Most of your carbides, once you wear it, it doesn't last very long. I think a lot of it's for beauty. And then, like I say, you have a titanium carbide and also that's a diffused titanium. But anyway, those are some coatings you can put on. Now I pulled this out of one article. It's an evaluation of some wood turning tools, the various brands, the chemical composition, and the probable steel. One thing that's interesting is you go down there, and the majority of them are an M2. There is an M50 in there, which very close to an M2 for your chemical composition, nothing special. I read the article, the M50 from the Craftsman, they said was the wrong application for it. And Shopsmith, M2, a lot of them are very similar. Grizzly, it has some lead in a minute. It's nothing special. The HSS is nothing special either.
How do the top two compare?
Top two, the top two, the Packard, that is very, very good. You can tell it's very good. You look at the cobalt. It's 10% cobalt. Cobalt's extremely expensive. You look at your vanadium. Vanadium is extremely expensive. You're going to get a very good tool. You don't put that kind of material in there without expecting good properties for it. Of all of those, the top one is really a premium.
Question.
Yes.
I've read these past, and I don't remember the letters and the numbers, but I was thinking it was with Lee Nielsen's and their plane irons. They feature a patented steel that uses the letter BM1 or something. Are you familiar with that at all?
I've heard of it,
I
yeah.
didn't know what the composition of that was that set it apart from. Supposedly it was very hard, and it stayed hard. You know, typically when it's real hard, it's hard to sharpen. But this had the property of the one where it was easy to sharpen, but yet you still had the property of extremely hard. And I didn't know how that compared with some of these products, but I didn't know what the composition was. It was a patented product, and I didn't remember.
I have a slide here at the end that shows some brand, a specific brand of tools and how they compare for composition. And these are generally, everybody takes a common alloy and tailors it to what they think is good. The chrome may be a little higher, vanadium a lower or higher, and there's lots of special alloys. Every time they make it special, they sell it to somebody, and yeah, this is patented and special properties. Yeah, they're enhanced, is what I like to say. Okay, here's another one. You know, some of your common ones here you'll see. The top ones, your M2, 3, and 4. See, the vanadium is a common alloy. Here's your tungsten. Tungsten's very high. Your chrome. Like I said, the carbon with the chrome, tungsten, and vanadium form carbides. Carbides are very small, very hard particles. And that's what gives you your wear resistance. Here you can see the hardnesses of those, 64, 66, 65, very hard. You go down to the bottom, and what those are, the PMs, like that PMA11, a lot of people do a PMV11, they're special alloy, similar to that. And what you have is, those are all powdered metal grades, the bottom 4. Powdered metal is very nice in that, we'll look at this and I'll go into the details of your powdered metal and what makes it superior. Your high speed, your properties typically, your toughness, the red hardness is what is nice here. Red hardness is when the tool gets hot and the tip, when it's cutting, it resists temper back or softening. And you see they're all pretty good. Your powdered metals are pretty good too. Basic chemistry, just a different. Therein sees ease of grinding. M4 isn't the best. Powdered metal, M4 looks pretty good. Now the reason the powdered metal M4 grinds so well is the carbides in it are very small and uniform. You don't have big chunks in there of carbides. They're very small, very fine, so your tool can actually cut them well, but when you're running them against wood, etc., they're very abrasion and resistant. There again, your carbon steels, your high strength or high speed steels. Next comes your carbides. Tungsten carbide's probably the most common one you'll find. Then you can get into some ceramic and diamond. Your ceramics and diamond tend to be for metal. But you can turn, with the ceramic, you can turn a Rockwell C60 heat treated part. Just like nothing. Yes?
There's some carbide saw blades on the market, real cheap.
Yeah.
There's a carbide, and then you get a $100 carbide blade, you get a $30 carbide blade. Is there a difference in the carbide?
Yes. In my lab, I buy carbide blades for cutting hard stuff, like a crankshaft. You can take a bandsaw blade and cut through it, and they're running Rockwell C55. They have different carbide grades for the tips, and the way they grind them, the throat in them, etc., determines, the performance of the blade. There's a big difference in price between the grades of carbides that are on the tip and their performance. And I really like them, your carbide ones, except they're extremely hard to use, especially for metal. You have to be real careful when you feed it in, the thickness, you don't chip them or break them off. A new one, huh?
I've seen that label that you mentioned, Bob, about the carbide being a C3 or C4.
C3 or C4, yes.
The degree of hardness then, or?
No. I have that later in the slide. There's 1 through 4, and one end of it is high toughness, the other one's high hardness. So you balance one against the other in choosing them. Your microstructures. This is a conventional, like an M2 probably, or an M4. You can see in the rock product on top, it's elongated. The carbides are longitudinal, the whites. In the powdered metal, It has no directionality. It's nice equiaxed. No matter where you cut it, you're going to get nice, fine, round, dispersed carbides, which means the properties in all directions are the same. You look at the size and uniformity of them, it's nice. Some others, there again, there's a wrought one. You see big ones. That's an end on. And you see big ones, small ones, some areas with them, some without. They do vary a fair amount. Once you get into a powdered metal, that's an M2. You can see they're all about the same size, uniformly dispersed. Another thing about these microstructures is those carbide particles are very hard. Those carbides will run somewhere around 70, 75 Rockwell C. And then the matrix is probably 58, 59 Rockwell C. The matrix is there to hold the carbides. And then the carbides do the work as far as cutting and resisting wear. This was a report I ran across on common steels for turning blades, you know, lathe tools. He set up a test, bunch of different materials, went in and machined to a given depth, same piece of wood, repeated it. He monitored the power usage, your amperage, as well as the wear on the tools. And here are the different materials he tested. What you see here in this graph, the current on the left is the amount of power it took to drive and machine or turn the wood out. So you'll find your M2 had the highest amount of force required, and your 15V and RX 86 had the least amount down here. On the bottom axis was the amount of wear. There again, the 15V and the 86 had the least amount of wear. The M2 had the most. If you look at, oops, here are the different tools, the tips of the tools he used to machine. Your M2 shows the amount of wear they had. As you go down, the last two show very, very little wear. You can see the grind marks still present on them. The M2, you can't even see any grind marks left. They've worn away. So that's kind of a way of showing your better, your higher carbide ones, which are on the bottom, resist the wear much, much better than the others. I found something on router bits. You know, you have high speed carbide tip and solid carbide. I'm not going to bore you with going through them, but as you start at the top and go downward, the cost increases. And you wonder where the cost is. Here's your router bits, the materials. The bit materials, you can have your first one of the three, your carbon steel, high-speed steel, and then some casting. But then the carbide itself, there's tipped carbides where they take a small carbide tip, braze it to a base, and the bases can either be fatigue-proof. That is a trade name for LaSalle steel. It's an 1144, resulfurized medium carbon steel. 4140 is a very good heat-treatable material. And then your best is the H13. Then they braze the carbide tip to that piece of metal that holds it. And then you have silver braze and you have a nice little tip. The better ones or more expensive ones, you go to a micrograin carbide and the whole thing is carbide. it's brazed right to the holder. That's where the money is, a big piece of carbide. But it'll last a lot longer and can be sharpened. Then I say from there you can go on down. The bottom three are more industrial. Cabinet maker would put those in for routering or something. Thousands and thousands of pieces. And then you can add surface coatings. Carbide tip saw blades, you know, they last 10 times longer. They have the durability. They're tungsten carbide, and they're a powder. They're made as a powder. They're powdered metal. And hard, they're cemented carbide. They're brazed on. You can get 4 different grades, C1, 2, 3, and 4. And you'll, in there, you know, the C4 is the hardest and the most brittle. The C1 is the softer and it's more ductile. So you balance your susceptibility to breaking the teeth versus the extended life of the blade. Like I say, it's a balance. Everything with these parts is a balance because high hardness is brittle, lower hardness is wear resistant. You lose your wear resistance, so you have to find the happy point. And some questions that Bob gave me. Your flexible carving tools, etc. There's a product out there. It's called Scaleless Blue Temper. It's like a 1074 steel. It's quenched and tempered, and it's about Rockwell C52 to 53. Now it's not martensitic, it's os tempered, so it's like a spring steel, very flexible, yet it has high hardness, and it's very sharpenable. You've compromised the hardness a little bit because you can't get that flexibility. Your os tempering heat treatment goes up to about 52, 53. That's optimized. Above that, they get really brittle.
The reason I asked that question was, Sid probably knows about it, what the answer said, but I've seen carving tools, like 6 carving tools, $800. What's going on here? What are they made of?
Yeah, they're not out of this. Yeah, yeah. Either that or they have a real good salesman. Yeah. Buyer, yeah. But yeah, those would have to be some real exotic to pay that much money.
What does it say?
Your common tools.
Not the $600.
I looked up the common carving tools. A lot of them tend to be a high carbon spring steel, os tempered, so you can get your os tempering. You can do other steels to os tempering. Gives you your flexibility. They're a little softer, so you'll have to sharpen them more often. But you need the flexibility.
Is that your flex cut? Is that the brand
Yeah.
you're talking about?
Mm-hmm. Yeah. I know the material they use for them, you can actually buy it in rolled up strips. And you can actually run through a punch press, and you can actually punch a hole in it, cut it off, etc., and not break it. But yet it is, like I say, Rockwell C53, 54. So it works pretty nice. It's got a nice tailored property. Diamond hones and stones. What you end up with is there's 2 kinds of diamonds. One's monocrystalline and one's a polycrystalline. Your monocrystalline cut much, much better. You can see the sharp points on them. They're very aggressive. They'll remove lots of material very nice. Polycrystalline are used quite a lot. in the lab for polishing, I prefer the polycrystalline. The reason being, when I section a piece of steel, I'll go in, I section it, mount it in epoxy, then you polish it to, you start out with grinding, you go to like a 320, 600, 800, 1200 paper, and a 2400 paper. Then you go over to a 3 micron diamond. But the polycrystalline will give you a real mirror finish, but it doesn't cut fast.
How do you know what you're getting when you buy a diamond mold? Whether it's mono or poly?
You have to do a lot of research. Yes, yes. If you're, if it's lower cost, you're probably getting the poly. And, you know, for like a honing stone or something, it's probably a poly. It's a lot lower cost. And let me see, what else do I have? Okay, this one I put on there, I found very interesting. I can't remember the supplier, but the supplier had all of these grades of carbides. Z14, Z9, you can read them all down there. Those are different ones he sold. But as you go, your ANSI standards, the first 3 fit the C2 or C1, C2, C3, C4. So what they've done is taken the C1 and came up with 3 separate variations of it to optimize the properties or for salability, you know. You look at the C2s, there's 3 of those. Same way, your ANSI and ISO. Your ISOs, you know, 40, a couple 30s, 320s, 10. That's the ISO standards. But they've taken a common grade, trimmed the alloys in them the way they wanted, and then gave them a special code of their own. So when they say, okay, it's got C2 on it, C2 has a lot of variation within the composition. But the general C1 to C4, the same thing you can see here. Impact resistance, C1, those are tougher. As they go up, your hardness gets higher as they go down and resist wear. So it's a balancing act. Any specific questions on any other? Yes?
I ran across a man at an auction who was buying up old planes with the Stanley Sweetheart logo on it, and his rationale was that the iron used in the cutters was original mined iron, not scrap steel, and it was therefore better. Does that make sense?
No. Not at all. The reason I say that is I've worked at John Deere for 40 years, and in that 40 years, the steel quality has gotten very, very good, especially in the last 10 to 15 years. If you're making steel for a given product, let's say a crankshaft, I have seen a good steel mill like Timken, they have made 40 heats, 2 different facilities, and from heat to heat, the chemical composition was so close you couldn't tell the difference between them. It was within check analysis. Cleanliness of steel is much, much better today. It's extremely clean. You go back 40 years, the cleanliness is not as clean. There's a lot more inclusions. Chemical composition, the variation is much, much greater. It's within the limits. If your limits are like this, 40 years ago, they'd use this much of them. Now, they use about this much. They're on a very narrow band. So your modern steels are much better than they were in the past.
What about the thought process back in ancient time where they made a sword and they kept folding it?
Oh, the Damascus type and or the layering, yeah.
Millions of layers or whatever.
Yeah, those are real interesting how they do that. What they were doing is they were laying them out, folding it, and you did decarburization on the surface. So you'd fold it together. So you'd have high carbon, low carbon, high carbon, low carbon, and you get this sandwich. So you had the high carbon layers in there for the hardness and wear resistance. You had the low carbon in between for toughness. I was at a symposium and they were looking at the layering in steel, how it affects stuff. They actually made some like that, except they took some really nice tool steel type and layered it with the plain carbon steel, just like that. Folded it, ran it through rollers hot, and beautiful properties. There's some knife makers who are using that now. They're actually layering them. Take sheet metal, grind them, layer them, put them in a stainless steel envelope, evacuate all the air out, heat them up, run them through a press, or a roll mill, and it'll actually bond them when they're hot. Make beautiful knives. I've seen some, or pictures of them.
Mike, you talked about this powder metal that they press and sinter
Yeah.
and make these new steels with. I always wondered, how do they make the powder, the iron powder?
They atomize spray it. They take liquid, drop it through, atomize spray it, and I think there's some water involved on occasion, a mist or something. Then they classify it, shake it out, regrind what isn't. There's so many different powders. Some are pre-alloyed, where the powder is the actual metal that they want. Others, they take 2 or 3 different powders, mix them together. When they sinter it, they diffuse together and form.
Some steel, some processes, they actually take powdered steel and they injection mold it and they heat it in the furnace. Is that, what kind of process is that?
That is another way of doing it. There's 2 ways to make powdered metal. One of them, you compact it, you have like a little briquette, you run it through a furnace, sinter it, and it has porosity in it. The other way is to mix it with a plastic, injection mold it in like a plastic forming, then you take it out, and the next process,
You gotta go in an oven. It has to go into an oven after that.
yeah, they have to sinter it, but I can't remember if the solvent extracts some of the binders that they use to inject it or not. Then it goes into an oven. Very nice process. The only tricky part of it is you get a fair amount of shrinkage.
Like a carbide saw blade, after you use it a while, especially with like pine, has a lot of sap in it, you get a buildup on the blade. You can buy manufacturing type cleaners to clean that off, that claim they don't harm the resins that are holding the carbide together. I use ammonia and 409. That's not going to hurt any of the...
No.
Deteriorate the carbon blade.
No. Your carbides are sintered and they're bonded by welding themselves together. particle-to-particle bonding. You know, they don't have any resins in them. The only time you get into resins are in grinding wheels, and then you have vitreous, or you've got various organic bonds in them.
Is that one cleaner, perfect?
That is sodium hydroxide. I would, huh? Yeah, it's a lye, yeah. It's a sodium hydroxide, yeah. I don't know, I'd have to look that up. I've generally just taken a wire brush or brass wheel just to brush it off. You use a brass, you know, wire wheel. Doesn't dull the, it's soft enough that it doesn't hurt anything. Doesn't affect the brazing or bond.
Mike, we probably should shut it down here.
Okay.
If there's any more questions, you can talk to Mike after.
Thank you, Mike.
Thank you for coming.
Thank you.